All right. Well, the reason why you're here this evening is because of this gentleman he is one of the world's leading volcano researchers. He is currently a professor at Uppsala University in Sweden and formerly also a professor in Trinity College in Dublin. And he is a member of the Fellowship of Royal Geographical Society, and he's a fellow of the Royal Society of Arts. And tonight, his first conversation this voyage is entitled The Ancient Volcanoes of Northern Ireland and Northwest of Scotland. So please put your hands together for Professor Valentin Troll.
Thank you, Dave. Thank you for the kind words, and thank you for joining me this afternoon. So yes, I'm a volcanologist, and I deal with volcanoes every day, all day, too much if you ask my wife. And today I'd like to talk a little bit about ancient volcanoes. This is how I started as an undergrad, looking at ancient volcanoes. Many volcanologists actually learn on dead volcanoes, like doctors. And you look at these old volcanoes and you think about how the bowels of a volcano operate and how it actually comes to an eruption. And this is where I started as an undergrad here in Scotland. And then I moved further and further to the hot spot, literally speaking, and that's Iceland. And the last 2 years I've been doing a lot of work in Iceland. And the conversations I'm gonna offer, they will move with the journey. We'll start with the ancient volcanoes, and then we're gonna look at submarine volcanoes in the Atlantic on our sea day. And then just before we reach Iceland, we're gonna look at Icelandic volcanoes. And the last conversation is about the recent eruptions that's been going on the Reykjanes Peninsula, and that's the most exciting lecture. So I really hope you can bear with me until then. So today I'm gonna talk about ancient volcanoes, but I'm gonna be very upfront about this. I have a few little messages that I wanted to slip in. I wanna say a few words about climate in the past. I wanna say a few words about, living beings and the connection to volcanoes. And I am very keen to kind of bring a few extra messages, not just about volcanoes, but about bigger picture things. So if you feel you need more information about any of that, please ask me, of course, and I'll be around until Reykjavik. And I'm gonna start here by mentioning large igneous provinces. Geologists call it lips. And what is that? Well, it's large, obviously. Igneous is Greek for fire, and province, well, that's a region. So large fire provinces, if you will. Large igneous provinces are actually areas in the world where we had intense volcanism for, geologically speaking, a very short time. Well, geological time is different to normal time. Short in geological time is 1 million years. So we had a period of 1 million years where volcanoes were going all crazy, and we have a number of areas in the world. I'm gonna pick out 4 of them here. So we have what's known as the Siberian traps, and we have the Deccan traps, and here where it says NAIP, it's a little small, the print, but I hope you can see it. That's the North Atlantic Igneous Province, and that's where we are right now. And there's one over in the northwestern US, and that's the Columbia River, and that's actually where Yellowstone is part of. There is one in Canada as well, but it's so far north you can't see it. It's the high Arctic lip, and one of my colleagues couldn't resist. She wrote a paper about it, and she titled the paper, The Stiff Upper Lip, because it's very cold there. But a serious point at the side. Here's a small inset here, and here it says something about extinctions on the genius level. And that means, well, whole areas of the animal kingdom dying out. And there's million years before present. And the red bars, they are lip events, large igneous province events. And the blue kind of spikes, they are the rate of extinction. And if we look here, we'll come here to this part here, this big blue spike. It says Deccan here, very small, and North Atlantic Igneous Province. There's 2 lips that happened close to each other, side by side in time, on the back of each other. And that's been very serious. But the biggest extinction event in the geological history that we are aware of is actually this Permian event here, and that's a little older. So here we have the not the Deccan traps, the Siberian traps. So it's these lavas over here that caused all the damage. So when people talk about dying of the dinosaurs, well, that happened really at this point. Sorry, let me bring you over here. That happened here at this second biggest spike. The biggest spike was much earlier, and a lot of marine animals got extinct at that point. So when it comes to the dinosaurs, many people claim it was a meteorite, but here's a problem. We don't have a meteorite with each of these extinction events, but we have a big volcanic province to go with each of them. So, one key point to take away, it's not the meteorites that cause extinctions. It's the volcanoes. It's pretty obvious. So, we're here now, and I'd like to talk a little bit about this time bracket here and how it relates to this part of the world. And here's just another graph. This is the number of marine animal families that got extinct. And once more, just to bring that point home, here's the Permian event, the Siberian traps, and it causes this big downturn in animals in the ocean. And this is actually the one that killed the dinosaurs. Comparatively small, but very effectful. So this is where we are, and I'd like to hone in onto that time period in the Earth history now. That's the end of the Cretaceous and the beginning of what's nowadays known as the Paleogene. And when I was a student, it was still called the Tertiary, but then somebody decided to change the name, and it was a bit, well, hard for me to get used to this. So here we have the time scale. Mesozoic goes up to the Cretaceous, big extinction event that killed the dinosaurs, and then the Cenozoic starts, and this is now the Paleogene era. But as I said, I grew up with it being called Tertiary, so I still like to sleep it in. Here's the spiral of time, and you might have seen things like that. This is the Earth history, and the Earth is about 4.6 giga-years old. That's 4,600 million years. Well, humans are on this planet only, well, humans as we know them, humans like us are only on this planet for less than 200,000 years. So we are really a very young invention. The time period I'm going to talk about now is actually here in that bracket here. That's when Earth history really starts to get exciting at about 65 million years. And this is when everything changed, certainly for us, mammals, and I'll talk more about this later. So, I want to also slip something in about temperature, because there's this argument, well, the atmosphere is heating up, we have climate issues ahead, and a lot of geoscientists say, well, wait a second, there has been periods in Earth history that were a lot warmer, and that is very, very true. We have two of those periods here. So, this is where I want to draw your attention to. At this time of the dinosaur extinction, which is about 65 million years, we actually were preparing for a temperature spike. This is one of the hottest temperatures that we know in geological history. Right now, we are over here on the far end of this diagram, and it's rising, but we are miles below this spike that we had back in the Paleogene. It was so warm that there was palm trees growing at what's now the North Pole. So let's think about this, and I'll let you digest this a little, because we want to think about what's the meaning of this and how does it relate to our present situation today. So here's a drawn out diagram. It's the same thing. We have temperature on the left, time on the x-axis, on the horizontal axis, and here we have this area here. And I showed you there was two lip events, two large igneous province events. There was one here in India, the Deccan traps, and then one here in Scotland, Ireland, and Greenland, and Canada. And then we had this spike. So both of these events were pushing the Earth system towards higher and higher surface temperatures. What was different back then? Well, geologists, they often like to think about plates moving around, and indeed, plate tectonics plays a role, but it's not the whole answer. But let's start with that. Well, we had one giant continent about 200 million years ago. It's called Pangaea, all Earth. All of the Earth together, meaning all land masses were combined. This is what I'm showing here on the left-hand side. This continent started to break up in the Jurassic period. That's where the dinosaurs were really strong. Well, Jurassic Park, you all heard of it. So, and it started off with splitting the north and the southern part of the continent, and then the southern part was splitting up and the northern part followed. Geologically, this takes a long, long time. It takes tens of millions of years before such a process is completed, but it started back in the Jurassic, and this was a major change at the time. How do we know about this? Because when we look at the ocean floor, we can actually measure the age of the rocks on the ocean floor. And when we do that in the Atlantic, here on the right-hand one in color, you see that the rocks in the middle of the Atlantic are very young, 0 age almost, and then towards the fringe, they get older and older. And that meant that the plates were gradually splitting apart, and the oldest rocks are now at the fringe of that system, while young rocks are actually produced in the middle. And we'll mention that a little bit more in detail when we talk about the Atlantic, but there's a large system going through the Atlantic, like a spine, the mid-Atlantic ridge. And that's where the Atlantic is spreading with about 2 centimeters a year. 2 centimeters a year. It's hard to kind of grasp, isn't it? Let me give you a flavor of this. 2 centimeters a year is the speed with which your fingernail grows. So that's the speed with which the Atlantic is spreading. The Pacific spreads a lot faster. The Pacific spreads about 7 centimeters a year. That's about the speed with which your hair grows. So that gives you a sense of that. And that's been going on for quite some time. In fact, for about 100 million years. But there's something else. And we're going to Iceland, so I'm going to highlight Iceland here. There's this one place in the North Atlantic, along this mid-Atlantic ridge, that really sticks out, and that's Iceland. What is going on there? Well, there we see this breaking apart of the plates. It's really obvious there. Here we have these large fracture systems that go through the entire country of Iceland from the south to the north, and we have a lot of volcanoes along this system. And this is the mid-ocean ridge visible above sea level, and it's there because there is an anomaly under Iceland. We call it the Iceland plume. And this is very important. You can really see on the right-hand map, there's this red ridge that goes from south to north, but then round about Iceland, we have this building up of material, of rock material, of course. This is built from lava, and Iceland is really sitting on this. So Iceland is like a spot that comes through this crack. And in a first-year geo textbook, it would look like this. We have this fracture system in green, and we have this heat anomaly sitting on the Iceland that pushes up. And this is one of the main reasons why Iceland is growing faster than the rest of the Atlantic. In reality, it looks a lot more complicated. So I'm going to give you a glimpse of that. That's how we picture it to look in reality. So there we have a whole system, and it's actually a little bendy. It's not coming up straight, and it sits right under Iceland right now. This hotspot, this anomaly, has been the main reason for the large igneous province of the North Atlantic, and has been given rise to the old volcanoes of the system, as well as the new volcanoes that are currently erupting, for example, in Iceland. So, where did the rocks of this event really get deposited? And here in pink, this is a very simple map, but the initial plume or hotspot material that was rising up due to the crack in the Atlantic, it was coming out where Iceland is today, but it spread like a mushroom under the crust. And we actually have volcanics in East Greenland and West Greenland. We have some in Canada, in Baffin Island, of the right age and the right composition. And we have them also submerged in the Atlantic, and we have them in Scotland and Ireland. That's the little pink splurge there in the lowest part of the circled area of the map. So how does that kind of come about? Well, the idea is that there was, of course, a plate, and the plate is brittle, it breaks, and it has thin and thick spots. And when this plume comes up and spreads like a mushroom, it will exploit these thin spots. And Scotland has had many mountain building episodes before. There was a lot of fractures there, and that's where some of the earliest volcanoes rose up, because of the fractured bedrock in the area. So this is a more geological map, and there we have Iceland in the center, and the red and pinkish areas are all rocks that link to the North Atlantic igneous province. It's a rather extensive province, and in terms of entire volume, it's as much as the entire island, the big island of Hawaii, for example. So it's a large amount of volcanic rock that was produced at the time. So I'm going to introduce you to all the Scottish and Irish volcanoes now, but before we do that, I'd like to kind of give you a quick introduction to the two types of volcanoes we find in Iceland, but also in this part of the world. And wherever we have these big cracks, these rift zones opening up, we get fissure volcanoes. These are fractures that open up, and they emit lava along these fractures. That's what's going on right now on the Reykjanes Peninsula. These look spectacular, very beautiful, but they're rather harmless for most parts. The big eruptions are actually the stratovolcanoes or central volcanoes. They often erupt much more explosively, they are much bigger, and they are the ones that cause air traffic problems, etc., etc. So right now what's going on in Reykjanes, that's the one on the bottom right-hand side. It's a rather manageable eruption. But in Eyjafjallajökull 2010, we had the situation on the left. But mentioning Eyjafjallajökull, this is actually Eyjafjallajökull 2010, and it's a little video. Let me share that with you. So if we look at the video, we can see both. Here's a little fissure eruption. There's a crack here on the side of the mountain, and the white steam that comes out, that marks the fissure eruption. And that vent up here, that's the central vent. So here we have a fissure eruption and a central volcano eruption at the same time. And I hope I get the video to work. So just a quick impression, but I guess you get the idea. And the central ones are the bigger ones. And the fissure eruptions, you could get close by, but the central ones, you want to stay away most of the time. So central volcanic complexes, and the map is very small because it's very overloaded with information. That's for geology students. We don't have to look at it in too much detail, but just to point out, each of the green splurges there is a central volcano. Each of the red areas is a lava field, a large lava field, and the little black stripes, they are fissures that are filled with lava, and they had fissure eruptions. So I'd like to take you now from south to north, and we're going to look at all these central volcanoes, at least very briefly. And I'd like to start with these, the Carlingford and the Slievegullien and Mourne Mountain complex in the borderlands between the Republic of Ireland and Northern Ireland. The boundary actually runs right through the kind of boundary between Slievegullien and Slieve Foy in the left-hand part of that map. And there we have three tertiary or Paleogene volcanoes. The Mourne Mountains are a little younger, but Slieve Foy and the Carlingford complex and Slievegullien, they're pretty much of the same age. And there is a ring complex currently exposed, and it's very nice hiking. It's also a natural park, and there's a lot of old legends to go with that volcano. I don't know whether you heard much about Hugh Cullen, the Irish hero. Well, the story goes that he started to like one of the local ladies, but the sister was a witch and she didn't like the attention her sister got. So she made herself into a fawn and she ran away. And Hugh Cullen was on the hunt, so he went after that. And he ended up on the mountain of Slievegullien. On the mountain, there was nothing to see, nothing to hunt, but there was a girl sitting at a lake and she was crying. And he asked her, "What's wrong?" And she points out her ring fell into the lake. And Cuchulainn, being a hero, he jumps into the lake trying to get the ring out, but by the time he comes up, he's an old man. So witchcraft made him an old man with white hair, and he couldn't really speak. Eventually, after all his friends came to help, he was kind of younging again, but his hair stayed white, so he's always depicted with white hair. And I'll let you think about what the meaning of that is exactly, but I think you may want to be a little careful with some adventures. So here is a few impressions, and it is a strange and eerie place because there's an old Neolithic burial tomb up there on the hill, and that's the little lake on the top left. I remember the first time I hiked up there all alone in the fog. It did feel a little spooky, I have to admit, but I didn't age very much at least, so. So, moving over to Carlingford, that's the next one. And here is also a mountainous area. This is the core of the volcano, the bowels of the old volcano. And again, there is an old story there. And this is the cattle rate of Cooley. And this is also a strange place for the simple reason that this is actually right at the border between Ulster and the Republic of Ireland. And the story goes that there was a conflict already back then in ancient times about who's got the strongest bull. And I'll leave the details up for you to explore if you want. But this is a very popular story up to today. So, but the area is also important geologically speaking, because there was where the first geologists defined what's nowadays known as ring dikes and cone sheets. Sheet intrusions that have circular surface expression, but they're either inclined inwards or they dip outwards. And there's different formation scenarios for these. So here again, we have a circular structure of the Carlingford volcano with different features and different rock types and a history, but a very short-lived history. Once more, this was all geologically very rapid. So, cone sheets, I found the original paper that produced the concept of cone sheets, and it goes back to this gentleman, Mike Labar. And I met him as a PhD student once. He was already very, well, dattery, but it was a great pleasure, and I managed to have a cup of tea with him. So, but he noted that if you put sheets into a volcano and they are inclined upwards, then they will actually cause the volcano to push up. And the important concept here was that he noted that volcanoes are not only growing by eruption of lava, they're actually growing by intrusion of material inside. So there is much being pushed up than there is material added. And this was the important realization that he made at that time. So this concept was later used to explain many of the rocks in the Mourne Mountains. This is a little bit further to the east, but in the same area. And there is a schematic sketch in the bottom right. And here we see these ring features cut in a section, in a vertical section. And this is how we picture them. And that's still pretty much spot on with our thinking today. The Mournes are very granite dominated, and it's now a geopark, and it's one of the European granite trails. So if you're interested and have the opportunity, very nice walking, beautiful landscape. And there is one spectacular place in the Mourne Mountains, and when I was working at Trinity, I was always bringing my students there. It's the lava lamp outcrop, as I call it, because there we actually have a situation where a mushy granite inside the volcano was intruded by fresh basaltic, fresh mafic dark magma, and then you get that blobby arrangement here, and this is really a frozen in lava lamp situation, as I would call it. So spectacular rocks, if you're a geologist. That really gets you excited. So we're moving a little further now. We're going to look at lava fields now, and the lava fields are quite large, actually. The Antrim lavas is the largest lava field, and let me just get the pointer up. So we're in this part now. So we're here in this part of Scotland, and we're just sailed by these volcanoes and the Antrim lavas. And tomorrow we're going to be in Mull. So there we're also going to have lava fields again. Actually, Mull is very nice because when you approach Mull and you see the lighthouse is already on lava of that time. So here we have the Cretaceous Ulster white limestone. It's the same as the Dover white limestone in the lower part, and the tertiary lavas, the ancient lavas, sitting right on top of this. And there you can get a sense of the thickness of those lavas. The most, well, formidable and probably most famous outcrop or rock occurrence there is the Giant's Causeway. The Giant's Causeway sits right at the very top here. It sits here at the Antrim coast, and there we have good exposures, and there we have lava with a lot of columnar jointing. Well, how do these columns form? I frequently get asked that question, and it's actually not that complicated. When material, hot material or wet material shrinks, then you get cracks, and that's really what happened there. When hot lava cools down, you shrink the material and you get cracks. If you have a puddle and it dries up, you get these mud cracks. It's the same phenomenon, only that it looks better in lava. So here we have the Giant's Causeway, and why is it called a causeway? Well, because there is a legend to go with that as well. It's not only a very popular holiday spot, and also has been very instrumental in developing the geological heritage in the area. But there is also a distillery on top of it. If you're interested, this is what my students at least call the true basalt whiskey. So this is the most geologically well-balanced whiskey that at least some people claim exists. So there's this story about the causeway. You may have heard about the other place that has a causeway, or is believed to be a causeway, Staffa. And we might just about kind of have a glimpse of Staffa when we sail by. There's another place like this in Scotland. And the two rock, they look very similar. But they're actually not of identical make. They're of different, slightly different times. But it's very tempting to put them together. And this is what this tale is kind of about. So the story is that there was this giant, an Irish giant, and he saw this small Scottish giant in the distance. And he thinks, oh, come on, he's just so tiny. I can go over and, knock him out of his seat. So he builds that causeway. But the more he builds the causeway over to Scotland, the more he realizes, this guy is not as small as he looked from a distance. So, and the closer he gets to Scotland, the more he realizes, actually, this is not a good idea. This chap is pretty big. So eventually he decides, I'll give up on this, and he runs back home and destroys the causeway after him. And well, the thing is that the Scottish giant, he's not stupid. He runs after him just in that final moment, and he arrives just a minute after him in Ireland. And being a bit out of its wits, the Irish giant decides, I need to play a trick. And he hides in his son's bed, and he makes himself really small, and he tells his wife, tell him that I'm not here, and that I'm the child. So a Scottish giant arrives and sees the child, and the child is pretty big, and then the Scottish giant gets all scared and thinks, if the kid is already that big, how big is the real giant? And then he runs back. So a story of confusion about size, and the causeway didn't survive. At the end of the day, the reality is the two things are not really connected. And I think that's the essence of the story, geologically as well as in other ways. So this is Staffa. This is the other causeway, and this is now in Scotland near Mull, and this is also a lava sequence, but it's not the same lava field. Let me stress that. So I'd like to move you to Arran just for a quick second, and we're very close to the Isle of Arran right now. It's another tertiary volcano, a big caldera, a bit like what we see at Yellowstone right now, but, well, it's not active right now, obviously. And we have a big granite there as well, the Northern Arran granite. It's kind of famous because it makes very nice water. So the water that goes through the granite rock is very clean and very pristine. And, well, what do you think people do with clean water in Scotland? They make whiskey, of course. So there's whiskey distilleries, Loch Ransa, etc., in the northern part of the island of Arran. But here's a bit of geology, and this granite here is world famous amongst geology students because it's the most circular granite we have. And this makes it a forceful intrusion. This granite didn't care so much about the surrounding rock. It just went there and took its space, and that's what is expressed in this shape. So iron is also important for this place. It's called the dune, the Drummond Dune intrusion, and this is a lava intrusion just below the surface of a volcano. It also has these columnar joints, but it's not a lava that flew on the surface. It was just a little below the surface, and it's a spectacular place for a hike. And there's also a golf course next to it. And surprise, surprise, they make whiskey there too. So, and coming over to Mull and North American, more whiskies. It's really quite striking, but I'm saying this with, a twinkle in my eye. There is a geological reason, because the bedrock has a huge impact on the water. It's like with wine, the bedrock makes a huge difference, and therefore whiskies grown, or where the water comes from volcanic rock, they have a somewhat different flavor. So Mull is a very complicated, big volcano, one of the biggest in the province. It had 3 major episodes. We call them ring centers, and they overlap, but they shifted a little bit. So the volcano is changing its focus on the map here. It goes from 1 to 2 to 3. It's moving somewhat towards the north, and we're going to come right towards this end. We're going to come in here, and we're going to look at the lava field here. But if you have a chance and make it further down, have a look at this mountainous interior as well. That's the heart of the old volcano. So this is just for geologists. This is bringing these rocks into different stages, just to give you a flavor how many hours must have gotten into that and how many geologists must have mapped this. But here is another little nasty story, and that is when the first British Geological Survey mappers, the first geologists were sent up there. The British Geological Survey was still practicing their mapping program, and they actually said they will pay the mappers an extra fee for each boundary they find. That's the result. So I think you could make it a little simpler, but that's what it is. I mean, people were making money by putting in boundaries, and what could be considered a rock type with small variations has then become a dozen rock types. So here's one of my favorite rocks, and this is on the Isle of Mull, and this is the Loch Ba ring dike, and this is the red. It's not quite circular, it's a bit distorted, but it's the red band there that spans around Loch Ba, the Loch of the Cows. And there we also have this magma mixing phenomenon represented. We have different types of magma in the same rock, and that is when a volcano was active, but new magma came in, and then the 2 magmas mixed, and it led to a big explosion, and that's what we see. This is not often the case at active volcanoes, but we know it happens, because we have this in the ancient volcanoes, for example, here in Scotland, but also in Ireland. And then the magma rises up and eventually erupts. So Adnamercan is right across the loch there, and there we have again the result of being paid by contacts. And there you see many, many boundaries, and people were mapping this in great detail. This is also a ring complex, very similar to the others, but it's world famous amongst geology students because of this great exposure of the rocks. So here we are. This is now putting colors on. Looks a little simpler, and the general concept is that sheets were coming up from a magma reservoir, and they were pushing the volcano up, causing eruptions, but also causing the volcano to grow internally. Now, this is actually the place where I did my undergrad mapping as a very, very junior geologist, the Isle of Rum. And the Isle of Rum is also known as the Forbidden Isle. It was actually privately owned, and you couldn't really go there for a long time. And it was owned by very rich people, the Bullocks, and there was a lot of weaving money behind this. And they built this in 1906. It was a complete well, jolly. And it had no purpose as such apart from making people happy. And nobody was allowed to go there. There are stories of extremely wild parties and all that kind of thing. Many people claim this is why it was not allowed to go there. But, well, I leave that up to you to make up your own mind. Geologically speaking, it's been a good thing because there is virtually no roads on the island. There's no cars on the island. There's 1,400 deers and 17 people. So it's a geologist's paradise. And here we have a central complex, beautiful mountains in the middle, and the mountains are actually the bowels of a volcano, the magma chamber of an eroded volcano, and there you can actually walk inside a volcano. So here we are. This is in red, the roof of the magma chamber that you can actually extrapolate there. The interior of the magma chamber is below, and we see that in the rock record. So here's a few impressions of how it looks. Many layers there because crystals, they settle out and they form layers and mushes at the bottom of a magma chamber. And this is a world-renowned place for this phenomenon. People come from far and wide to see these rocks, and these stripes are all layers of new material. So new magma was coming in, making one layer, another new pulse makes another layer, a new pulse again makes a third layer, etc., etc. So here we have 16 layers of activity represented, and it teaches us that volcanoes, they are episodic. This is an episodic phenomenon, and of course, that's what we see in many places. So when we put this all together, this was done by Graham, one of my PhD students at the time, and in red, the red dotted line is the current hillside, the outcrops of the current hillside, and this is how we put the volcano in there with a layered material from the magma chamber sitting right there in the center of the island. So there's a fancy mountain on the Isle of Rum, and it's called Trollaval. And well, I'm Val Troll, so I couldn't help. I had to climb the mountain. It wasn't really in my fieldwork program, but I had this Sunday afternoon, so I set out to climb Troll Val because I loved the idea of Val Troll on Troll Val. So I went up there, and I had a mapping student with me, Liz, at the time. Liz didn't dare to go up because it was quite a narrow ridge. But there on the right-hand side, you see Val Troll on Troll Val, trolls in their natural habitat. So here's another picture of that. And well, why is it called Trollval? Actually, it has little to do with trolls. It's because the island was used by the Norse, by the Vikings, as a navigational aid, and they stopped there every now and then to camp overnight. And this particular mountain made a lot of noise during the night. And the Vikings, oh my God, there must be trolls up there. So, but it turns out to be Manx shearwater, night-active birds, and they make a lot of noise. And the Vikings had no real clue, so they got a little frightened, I guess. So, thinking it was big trolls. But anyway, so let's move to the last one, Skye. The Isle of Skye is very famous, also for whiskey, but also for this place, the Old Man of Score. So this is one of the pinnacles that stands out in the north of the island, and it's part of the big lava field there. Again, a big volcano there. And again, many different units that have been mapped by many generations of people being paid by putting in boundaries. And so this is why it looks very complicated. But of course, there's a lot of useful information there for the geologist. So we understand these episodic buildups of volcanoes rather well. So this is the heart of the island of Skye, and on the right-hand side in green, the big lava field that extends towards the northwest. And there is one particular important whiskey that comes from the Isle of Skye, that's Talisker. And Talisker is the only distillery that actually sits inside the bowels of an old volcano. So if you want to have a magma chamber whiskey, then that's the one to get. So we're moving towards the final part now. So this is a bit of an outlook to give you a few other dimensions of things. And this is an island. We're going to pass the island of Egg. It's a tiny little island, but it's got this prominent ridge. It's a really long ridge. It's several kilometers long, and it's called the Skewer of Egg. It stands proud, and it's a very different rock type. And it's a rock type that we don't really see in the rest of Egg. The only other time we find that rock type is actually on a tiny little rock out there in the ocean, and that's here at the place called Oiksker. And we're going to sail by Oiksker. So have a look for it. And this down here is Oiksker. So here's 2 people for scale. And this is exactly the same rock type as we have on Egg. The problem is these 2 places are tens of kilometers apart. And they have the same chemical composition as a rock suite on Skye. So as a geologist, you have to draw the ultimate conclusion that there must have been a giant eruption on Skye that produced material that was flowing for tens of kilometers all the way to Egg and also to the other side of the Isle of Rum, to this place called Oiksker. And this was such an enormous eruption, therefore, that it likely impacted the climate. These eruptions are so big that they will have a climate effect. A single eruption will have a lasting effect for a few years. If we have a whole series of eruptions of this magnitude, this will swing things in a much, much bigger way. And now I want to come back to the climate changes that we see as part of large igneous province evolution. This is how it works. These eruptions are building up. They're producing a lot of CO2, a lot of SO2. They're pumping it into the atmosphere. The sunlight is not coming through. The heat that wants to escape is trapped inside the atmosphere, and things are getting extremely warm for at least a short while. And this is one of the strongest bits of evidence for these large eruptions to occur back then. I have left a few handouts there. There's the original article there, but there's also a few media, sensational kind of things. I think one of the media outlets called it the Scottish Krakatoa and other kind of claims. But, well, I think it certainly had a large impact, and these were very large eruptions with run-out distances of literally tens of kilometers. So here, BBC was a little bit more nuanced. They basically just said it changed the climate. But here is the climate or the temperature plot again that I showed earlier. It's just a little bit more complicated this time. Let me run you through this. So here we had 65 million. This is when the dinosaurs died. So this is when we had the first spike. This is linked to the Indian large igneous province, the Deccan Traps, and this is where the Scottish volcanoes erupted, and this is what I just described, this build-up of heat in the system leading to the Eocene thermal maximum, and this is where the Scottish volcanoes contributed enormously. So it wasn't the Scottish volcanoes that killed the dinosaurs. I can be confident about that. They did not. It was more the Indian volcanoes that did that, plus a little bit of meteorite activity and things like that at the time. But what did the Scottish volcanoes really do? Well, after the dinosaurs got extinct, something else happened, and that is mammals came up. And that's us, really. So, because of the Scottish volcanoes, the reptiles never really recovered. Because it was so hot, the reptiles couldn't actually, work with it. Mammals can. We can regulate our body heat a lot better. We can actually work a little bit with hot and cold. We don't have to lie in the sun in the morning to get warm and things like that. So these episodes of extreme heat, they were the demise of the dinosaurs. And it's not the lava that killed the dinosaurs, it's the heat they couldn't regulate. Whereas the little rodents, they could. And therefore the Scottish the Scottish volcanoes were instrumental in making a huge change. Many of the species that existed were out, and many others came in. The mammals got really strong. So after that, it was the mammals that became the ruling group of land animals. And this is what the Scottish volcanoes contributed towards our history. I say thank you for your time, and I hope you found this interesting.